right, Physics 1151. Today is Monday, the 15th of February. Going to be starting a new unit today, electricity and magnetism. So for about the next 6 to 7 weeks, we're going to be covering electricity and magnetism. Here's a picture here. We all know what this is. This is a lightning strike, right? And so lightning basically involves the transfer of charge from the base of a cloud through the air to the ground, right? And that's electricity. And so electricity is the result of charges which, through separation, move from one place to another, and they exhibit a variety of effects. So we're going to qualitatively discuss the origin of electricity today and the methods for producing it. This picture to the left here, H2O, water. So the origin of electricity is at the atomic level, and it's due to the fact that atoms have positive and negative charges called protons and electrons, and these give rise to electrical effects. So we're going to go over the origin of electricity. We're going to go into a little bit of why some materials are very good at conducting electricity, while other materials called insulators are not. And then we're going to go into a few methods for charging an object. Some of you may be happy. I don't think we have one mathematical equation in the whole set of notes. But I'm sad today. I had some demos that just didn't work out very well with the items that I had at home. So fortunately, YouTube and Bill Nye, the science guy, are coming to our rescue today. So let's begin here. Before we start talking about electricity, there's four fundamental forces in nature. And I know that you're going to say, oh, there's more forces. There's the buoyant force, and there's the normal force, and there's friction and the spring force. Well, at the fundamental level, they all are classified as one of four types of forces. Most of the forces that you have seen to date are gravitational, or are what are called electromagnetic forces. And gravitational forces arise because of a property that materials have called mass. And electromagnetic forces we'll see arise because materials have a property called charge. And so some of the forces, the other forces that you've dealt with, elastic force, normal force, friction, we'll see later in the unit. At the fundamental level, these forces are electromagnetic forces in nature. We're going to start simple, and we're going to assume that these charges are not moving, they're at rest, and this is called electrostatics. And then we'll get into moving charges and see that these give rise to magnetic effects, what we call the magnetic force. So here there are the four fundamental forces are called the gravitational force, the electromagnetic force, the strong force, and the weak force. And if we call the strength of if we normalize and say that the strong force has a strength of 1, the other forces are all much weaker. So let's start off with the strongest force. So the strong force arises, and it's the force that holds the nucleus of an atom together. It's like the glue of the nucleus. And if there weren't a strong force, we know that these protons in the nucleus, because they're positive, would repel one another and the nucleus would blow apart. But it doesn't. And so there must be a glue which tends to hold these protons and these neutrons together. And that force is called the strong force. Now the range of that force is limited. It's limited only it acts only a range of about 10 to the negative 15 meters, which is about the size of an atomic nucleus. So it's a very strong force, but we don't notice it because it acts only over such small distances. The electroweak force we're not really going to cover much in this class. It's the force on subatomic particles due to one another, and it gives rise to beta decay, on decay of nuclei, radioactive decay, and it acts over distances of only 10 to the negative 18 meters. And so over the distances that in our everyday world we don't observe this. The electromagnetic force, which is due to the fact that of a property called charge, positive and negative charges are attracted, charges of the same sign are repelled. This is a much weaker force. It's only at 1/137th as strong as the strong force, but it acts over a much larger distance. And so we can see this force, we can't see the force, but we observe its effects in our everyday life. And then gravity, the gravitational force, which arises due to the property called mass. This force is 10 to the negative 39 times weaker than the strong force, and it's about 10 to the 36 times weaker than the electromagnetic force, but it acts over large distances. So macroscopic objects, which have a lot of mass, were able to observe this effect, but when it comes to the molecular level, the gravitational force is about 10 to the 36 times smaller than the electromagnetic force, and usually we don't need to consider it when discussing subatomic particles or the atomic particles, because the electromagnetic force is so much stronger. So these are the four forces in nature, and in this unit we're going to focus on the electromagnetic force. So the origin of electricity is at the atomic level, and it's because atoms and molecules are composed of protons and electrons. And protons in the nucleus are positively charged, and electrons, which are whizzing around the nucleus, are negatively charged. And these negatively charged electrons are kept in their orbits by their attraction to the positively charged nucleus. And so, as a whole, each atom is typically found in a neutral state, meaning it has the same amount of protons as it does electrons. And so if we look at the periodic table, hydrogen has one proton and one electron orbiting the proton. Helium has two protons and it has two electrons. It also has two neutrons, but the neutrons aren't charged, and so we can neglect them when discussing electricity and just consider the two protons and the two electrons. Okay. Lithium, which is the third element in the periodic table, has three protons and three electrons, and so on. And so these atoms in their typical states are what are called neutral. They have the same number of protons as electrons, and so the net charge on a neutral atom is zero. Here's each of these protons and the neutrons that have a same magnitude of charge. Okay, so a proton and an electron. So a proton and an electron, the magnitude of the charge on each of these is 1.6 times 10 to the negative 19 coulombs, which is a big C, and that is the unit of electrical charge, is the coulomb. Okay, and so a proton and an electron each have a magnitude of 1.6 times 10 to the negative 19 coulombs of charge, but the proton has a positive charge and the electron has a negative. And we call this E, which is the unit of charge of a proton or an electron. Okay, 1.6 times 10 to the negative 19 coulombs. Okay. Now, if you look at the mass of a proton and the mass of a neutron, it's on the order of 10 to the negative 27 coulombs, And these masses are so small that if you calculate the gravitational force acting on these particles is negligible in comparison to the electrical force. And so here's a picture of an atom. In this case, the atom has 4 protons, 4 neutrons, and 4 electrons. And if you go back to the periodic table, that is beryllium. So in nature, the atoms are typically found with an equal amount of protons and electrons, but we can add or remove electrons from an atom, and therefore it gives rise to a net charge, which it allows it to attract other atoms and molecules or repel them. And so it's much easier to remove electrons than it is to remove a proton. And so molecules add charge by either giving up an electron or acquiring an electron. And for example, if you have this atom here, which has 5 protons and 4 electrons, and that is boron. Boron has lost an electron, it's giving up an electron, and it becomes positively charged. So 5 protons, 4 electrons, 5 minus 4 is 1, plus 1, and this ion has a charge of 1 e, which is plus 1 times 10 to 1.6 times 10 to the negative 19 coulombs. Now that's what's called a positive ion. It has a net charge of 1 times the charge of an electron. So here is the charge, 5, here's boron again, but here we add an electron to it. So now it has 5 protons and 6 electrons, so it's acquired a negative charge, and the net charge is 5 minus 6, which is negative 1 times E, or negative 1.6 times 10 to the negative 19 coulombs. And so this is a negatively charged ion, okay? And the atom on the left here is a positively charged ion. Now, since the amount of charge on a given atom or molecule is quantized, it can change by given multiples of the charge of an electron by adding or removing electrons. Okay. Now the law of conservation of charge says that charge cannot be created or destroyed, but it can be transferred from one object to another as electrons move about from one to the other. Okay. And so materials that tend to lose electrons easily become positively charged, and materials that tend to gain electrons easily become negatively charged. And if we look at the periodic table, materials or atoms here in the first row of the periodic table have what's called one valence electron, okay? Meaning their outer shell has 1 electron, lithium, sodium. And if you remember from general chemistry, atoms tend to be most stable and happy when they have a full shell. And so lithium will gladly give up an electron to a material like fluorine, which is 1 electron short of a full shell, or 1 fry short of a Happy Meal. And so when lithium and fluoride get together, or when sodium and chloride tend to get together, the atom on the left side tends to be more willing to give up its outer electron to make the atom on the right side here happy. So then they both have a full shell. And so sodium chloride, which is table salt, the sodium part of the molecule tends to be more positively charged because it gives up its valence electron, and the chlorine atom tends to have more of a negative charge, and that creates a separation of charge. So these atoms on the left side tend to give up electrons, and these that are the 7A atoms tend to acquire electrons. They want to have another electron to have a full shell. So if you look at some materials here, this is what's called a table of electron affinities. You'll be dealing with this in lab. And so these materials on the left side tend to have a high electron affinity. Air, human hands, asbestos, fur, glass, they tend to be more willing to give up electrons and become positively charged when you rub these with another material. Whereas these materials way at the bottom of this second are the most negative, they tend to want to acquire electrons when rubbing with another material. And so if you look at human hand, the human hand has a high electron affinity. It's willing to give up electrons easily because it's at the upper left of the table here. And so if I have a human hand and I rub it against a plastic or vinyl or silicon or Teflon, the human hand tends to give up electrons, and the Teflon and these vinyl tend to acquire electrons, okay? And if you've ever went down a slide and shocked a friend, which is one of my favorite activities, your hand, when you rub against most plastics, hard plastic materials, your hands tend to give up electrons when they rub against materials, and these plastic and vinyl materials tend to acquire electrons, and so your hand tends to acquire a positive charge, which you can use to shock your friend. Okay, so this is a table of electron affinity, and these materials here, that the further the upper left, they tend to lose electrons. These materials here in the middle of the table, the bottom of the left column, the top of the right, they don't tend to have a real strong desire to gain or lose. And as you progressively go down to the bottom right, these materials tend to acquire electrons when they rub against other materials. So we're going to get into an example. We're going to get into how electrons can be transferred by rubbing in a little bit, but let's see, basically, to get an appreciation for how big a coulomb of charge is, let's calculate how many electrons are in a coulomb. Okay, so each electron has a charge of 1.6 times 10 to the negative 19 coulombs. And so if we set Q as 1 coulomb and calculate the number of electrons N in a coulomb, we see that there are 6.25 times 10 to the negative 18 electrons in 1 coulomb. And that's a lot of electrons, right? So a coulomb is a pretty big unit, and so often we'll specify charge in terms of microcoulombs or picocoulombs or nanocoulombs, because 1 coulomb is a lot of charge. Okay. So let's compare the charge here on each of these systems here. So we're going to rank each of these systems, Q, A through E, in terms of the most positive to the most negative. Okay, so let's look at a proton. A proton has a charge of plus 1 E, right? It's 1 proton, and each proton has a magnitude of charge E, or 1.6 times 10 to the negative 19 coulombs. Okay. System B, an electron. An electron has a charge negative 1 times E, or negative 1.6 times 10 to the negative 19 coulombs. Now we've got an atom here which has 17 protons and 19 electrons. And so its net charge is 17 minus 19, or negative 2 times E. D has 1,000,000 protons, but it has 1,000,000 electrons too, and so its net charge is 0, 1,000,000 minus 1,000,000, or 0, and so this is a neutral system. and then you have a glass ball that's missing 3 electrons, and so its charge is plus 3 times E. And so if we rank these, system E has the most positive charge, followed by system A, which has a charge of the proton, which has a charge of plus 1 E, followed by D, which is 0 E, followed by B, which is negative 1 E, and which is followed by C, which is negative 2 times E. So the net, remember, we're always, when we talk about a charge on a body, we're always talking about the net charge, right? This system has 1,000,000 protons and 1,000,000 electrons, but its net charge is 0. So it's the net charge when we talk about Q, and that's proportional to the number of protons minus the number of electrons times the charge of each proton and electron. Okay. So now that we've defined, basically the origin of charges, how do charges behave? Well, if you have 2 charges and we put a proton and an electron, or a charge of plus 1 on this sphere and a charge of minus 1 on this sphere, and we put them together, they're going to attract, right? Positive charges and negative charges attract one another. Opposites attract, okay? If we have this system right here, we charge both of them negatively, they will tend to repel one another, okay? Negative and a negative tend to push one another apart. Same if we have a positive charge on one sphere and a positive charge on another, they tend to push one another apart. And so opposites attract, like charges repel, okay? So that's one basic property of charges, is that they attract the opposite sign charges and they repel charges of the same sign. Okay. Here's another example. If you take a comb and you rub it in your hair and you put a bunch of paper snips on a table, the comb is charged, right? The electrons are going to get pulled out of your hair onto the comb, but the paper is neutral. But yet the comb will attract the paper. And so neutral objects can be attracted to charge of either sign. We'll get into, that's due to induction. We'll get into that in a little bit. And then charge can be transferred from one object to another, but it can never be created or destroyed. And that's what's called the law of the conservation of charge. Okay, that says that charges can be transferred from one body to another, but they can't be created or destroyed. They're conserved. So the electrical effects of materials are much different depending if you have a material such as a metal or if you have a material that's an insulator. And so there are 2 general classes of materials. And so the first type of materials are what are called electrical conductors. And electrical conductors are metals and ionic solutions. And these are where electrons are free to move throughout the material and conduct electricity. And it turns out that the same materials that are good conductors of heat, namely metals, are good conductors of electricity. And this all arises because the electrons are free to move through the metal easily and conduct electricity. Okay. Now, other materials such as glass and plastic, most plastics and rubber, electrons have a hard time moving through those materials. They're bound to the atoms, and those materials are poor electrical conductors. In other words, electricity cannot flow through these materials, and these are what are called insulators. Okay, and that's why the wires in your home are made out of metal, copper usually, because copper is a good conductor. Electrons can flow through the copper. And it's also why you have an insulation around the wire, because we don't want the charges on the wires escaping and shocking you. Okay, so conductors are good, the electricity can move through them, metals, ionic solutions, um, and insulators, electricity cannot flow very easily through that. Okay. So let's talk a little bit about the ways in which we can charge and discharge objects. And the first way in which we can charge objects is we can charge them by rubbing. Okay, you can take a balloon and you can rub it with your hair, and you'll get electrons transferred from your hair to the balloon. Okay, and that's a way of transferring electrons from your hair to the balloon by rubbing, and that works really well for insulators. The second method that we're going to go into is called charging by contact. If you touch two bodies together, one of them can transfer its charge to another by touching. And that works well for metals, but not so well for insulators. And then the third way is we can charge an object even if we don't put them in contact to one another, and that's called charging by induction. So we're going to get into each of these three means of charging objects. So here's an example here. So here's if you have animal fur, so here's maybe your dog, and here you have an ebonite rod, or just think of a plastic rod or a PVC rod here, and we rub them together. What's going to happen? Okay, well, electrons are going to get transferred from the rod to the fur. From the fur to the rod, and the rod will be positively charged, and the fur will be negatively charged. Okay, so why is it that the rod becomes negative and the fur becomes positive? Okay, well, let's go to our table here. So here, hair and fur, these types of materials tend to lose electrons easily because they're at the top left of the table here. Okay, they have a high electron affinity. They tend to be willing to give up electrons. So hair and fur tend to become positively charged when we rub them with anything. And the other material, in this case, plastics, PVC, vinyl, anything that most rods are made out of, these tend to acquire a negative charge. They're on the bottom right of the table. And so when I rub the rod with hair or fur, the fur tends to give up electrons and be negative, and the rod tends to, and the rod tends to acquire electrons and become negatively charged. Okay. But the net charge remains the same. It's just electrons are transferred from the fur to the rod. So this is called transfer of charge by rubbing. Okay. So suppose we rub the balloon on hair. Let's make a prediction here. So suppose we rub our hair with a balloon, and then we rub the PVC pipe with a wool cloth. Okay, so we rub the pipe with a cloth, and then we rub the balloon with the hair, and then we place the balloon near the pipe. Okay, question is, will the balloon and the pipe experience an attractive force, or will they be repelled? Okay, so let's look at each of these individually. So first, let's rub our hair with the balloon. So what's going to happen? Well, hair is near the top left of the table, okay? And most other materials, rubbers, plastics, these materials are all near the bottom right. So the balloon, it's rubber or latex. The balloon is going to acquire electrons and become negatively charged, and the hair is going to become positively charged. Okay, so the balloon will become negatively charged when we rub it with our hair. Okay, now let's look at the PVC and the wool. So now we rub the PVC with the wool, and the PVC rod is near the bottom. This tends to want to acquire negative electrons, so PVC becomes negatively charged. Wool is to the left of PVC, and so wool will tend to give up electrons to the PVC when you rub PVC with wool. So whichever one is closer to the upper left will lose electrons. Whichever material is to the lower right will tend to gain electrons. So the PVC becomes negatively charged and the rubber or latex balloon becomes negatively charged. Okay? So what happens when we put the balloon near the PVC is the balloon has been negatively charged by rubbing it with hair. The PVC has become negatively charged by rubbing it with the wool. And if you put negative charge near negative charge, they will tend to repel one another. And so our prediction is that they will experience a repelling force. Okay, so no balloons at the house, so we have to call Bill Nye here. So let's watch the video here and see if our prediction holds.
Hanging by a string. There's an invisible field pushing the two balloons apart. When you rub the balloon on your hair, you're transferring electrons from your hair onto the surface of the balloon. Now, the balloon's made of rubber. Electrons don't flow through it the way they do through a metal wire. Instead, they stay on the surface of the rubber. We use the word static electricity, which means electricity that stays. Now, different materials have different properties. Here's a stiff rubber rod and a piece of fur. It's like rubbing a rubber balloon on my hair. It also will push the balloon away. But watch what happens when I use the same piece of fur and this glass rod. It pulls the balloon toward it. So in the first case, we say they have like charges, like static charges, so they repel. In this case, they have opposite static charges, so they attract. You can try different materials and different experiments. Here's some rubber making scraps of paper jump around. It's fun. Or you can try two at once. Here's a repelling rod and an attracting rod. Repelling, attracting, repelling, attracting. I'm experimenting.
Okay, so let's look at, okay, so our prediction was confirmed here. Okay, remember the balloon? We put negative charge on the balloon by rubbing with our hair, right? Because our hair tends to give up on electrons, and the balloon tends to gain it. The rubber latex tends to gain an electron, right? And so the PVC also tends to gain electrons. And so when we put the PVC, which is negatively charged, near the negatively charged balloon, negative and negative close to one another will repel, right? So why did the glass rod tend to attract the balloon when Bill rubbed the glass rod with the fur? Well, if we look here, if you rub fur with glass with fur, glass is more electronegative than fur. Or glass has a higher electron affinity than fur. Glass tends to give up electrons. Fur is lower in the table. Fur tends to acquire electrons when rubbed with glass. So when you rub glass with fur, glass is higher, closer to the upper left. Glass gives up electrons to the fur. The fur becomes negatively charged. The glass becomes positively charged. And now when I put the positively charged glass rod near the negatively charged balloon, they tend to attract, okay? And so the moral here of the story when using this table is that when you rub two objects together, whichever object has a greatest electron affinity, meaning closer to the upper left, will give up electrons, and whichever one of the two materials is closer to the bottom right will tend to acquire electrons and be negatively charged, okay? And so when I rub two objects together of different materials, one of these will give up electrons to the other, becoming positively charged, while the other material will gain the electrons, becoming negatively charged. And so you can play with these different materials and then put the charged materials close to one another and determine whether they will be attracted or repelled. And you'll be doing quite a bit of this in an upcoming lab on electrostatics, so I won't ruin too much of your fun now. So the first way of charging objects is to have them when they're rubbed together, okay? And we've all experienced that. A second way of charging objects, particularly metals, is to touch two objects together. Okay, and let's look at an example here. So suppose we have this same rod, and remember most of these rod materials tend to be negatively charged, right? When you rub them with fur, when you rub them with hair or anything, they tend to be have a most electronegative. They tend to acquire electrons, and so they're negatively charged. And so suppose we've negatively charged this rod, and then we put it near this metal sphere. What's going to happen? Okay, well, the key points here are that, remember, with a metal, electrons are free to move around a metal, right? It's a conductor, so electrons are free to redistribute themselves and move around the metal very rapidly. Okay, so that's the first key point, is electrons are free to move around in a metal. Okay, then we know that electrons tend to repel one another, and so if you put a bunch of electrons close to one another, they're not going to be liking that, right? They're going to want to repel and spread out to minimize the repulsion. So that's the second key point. And then the third is that with a metal, any unbalanced charge will reside on the surface. There will be no net charge on the inside of a conductor. So if we take this metal rod and we charge it negatively, and we touch the rod, some of this negative charge from the metal rod is going to be deposited onto the metal, or from the rod is going to tend to be deposited on the sphere, right? The metal sphere. So we're transferring charge from the rod to the sphere by contact. And once this charge is placed on the metal, the electrons are going to repel, and the charge is going to spread out so that it becomes as far away from one another as possible, okay? In other words, the charges will redistribute themselves to minimize the repulsions, okay? And so the charge tends to spread out all over. It tends to diffuse all over the conducting body. And so when we charge any metal, place charge on it, the charge will spread out and diffuse over the surface of the metal. Okay. Now what happens if we have that metal and we place some positive charge, here we place some positive charge on the metal, and that metal touches another conductor, like maybe you. Okay, so you might say, well, I'm not a conductor. Well, you are. Okay, so the human body is able to conduct electricity because there's a slight imbalance of positive and negative charge inside and outside the cells. Okay, so we tend to have this ionic charge, and so human body is a good conductor of electricity. And so if we touch the metal, now you have two conductors in contact. And so two conductors in contact, this positive charge wants to minimize the repulsion, right? They're like charges. They don't like to be close to one another. And so they're going to spread out and diffuse over both conducting bodies, the metal and you, okay? So what we've done now when two conductors are in contact is the charge spreads out, and the net charge spreads out, and it's shared between the conducting bodies. And so, in other words, we've discharged some of the metal onto the body, which is you. Okay. Now, if you're not in contact, if you're suppose you're standing on a rubber mat. Okay. Remember, rubber is a poor insulator, so this charge has nowhere to go. It's on the surface of your body, and it's on the surface of the metal, okay? And so the charge is redistributed between the two objects, okay? If you tend to touch the ground, this has a path to ground, and we'll see that the electricity will discharge through you, which is often a bad thing. Okay, so the human body is anytime you have two metals or two conductors, and there's a net charge on one, and that touches another conductor, that electricity will discharge. Some of it will discharge onto the other body. Okay, and so the human body is a good conductor. So anytime we touch a metal that's charged, some of that charge will dissipate onto us. Now the earth is also conductive, okay? The surface of the earth tends to be negatively charged, and the interior of the earth tends to have a net positive charge. So the earth as a whole is neutral, but the earth's surface and near the surface tends to be this huge reservoir of electrons, okay? And so now what happens if we take the rubber mat off of you and we allow your feet to be in contact with the earth? What do you think is going to happen? Okay, well, let's see. The electrons from the earth will tend to be attracted to the positive charge on your body and on the metal, and so they'll rush to neutralize this charge, which is the same as the positive charge going from your body to the earth. And so the electricity will discharge from the metal through your body to the earth, and you will tend to be shocked because the electricity has a path from the metal to the earth through you. Okay, so anytime metals are in contact, or any conductors are in contact with one another, any net charge on one of them can be dissipated onto all of the other bodies. So let's look at a good example of it, is a lightning rod. So let's suppose here that we take this metal rod and we connect it to our roof, and then we hook it up through a wire, and we hook it up to a metal rod which is buried into the ground. And this is what's called the grounding rod. And now suppose that lightning strikes the rod, what's going to happen? Okay, well, there will be charge attracted to the rod. The rod is connected to the wire, and so the charge on the rod will go through the wire. The wire is connected to the metal grounding rod, and so the charge will be dissipated from the rod through the metal wire to the rod, and the rod is buried into the earth. And remember, the earth is a big reservoir of charge, and so we can easily bleed this charge off into the earth without it having any real effect. And so the whole point of a lightning rod is to attract this charge from a lightning strike so that it doesn't strike the building, your house. So we have this pointed rod, and it's at a height greater than the building, and so the goal is to attract this lightning strike, and so the charge can bleed harmlessly to ground. And we say that the lightning rod is grounded, okay? So anything that's connected, any metal that's connected through a wire to ground, we say is grounded. And the whole purpose of that is to prevent charge from building up here on the roof or anywhere else on this building in your house. So it's harmlessly bled to ground. Another example is a three-prong plug. Okay, if you have a three-prong plug, the third prong is a ground connection. And that ground connection is connected to a wire, and that goes to one of your copper pipes, your water pipes, and that's connected to ground. And so that bleeds charge from an appliance. If any charge were to build up, that would bleed the charge to ground. It would discharge to ground without shocking you. Okay, and so anything that's physically connected to ground, we say is grounded, whether that be a lightning rod or the third prong on your plug that's connected to the wire, which is connected to a metal pipe, which is buried in the ground. That just provides an easy path to ground. Okay, so here's a question. You might have heard that it's better to stay in your car when there's a storm out and there's lightning outside. Why is that? Okay, so what happens if you were to get out of your car and touch the metal chassis of your car? Okay, what would happen? Okay, well, you touch the metal body of the car, and if there's lightning, charge builds up on the car, right? If there's charge, that charge wants the easiest path to ground. And it can't get to ground through the tires because they're rubber. So if you touch the metal, it's the easiest path for this charge to go to ground is through you. And so the charge will go from the metal frame of your car through your body to ground, and could die. Okay, so a current would flow through you, and so that's why if there's ever a storm, you're better off to stay in your car than to get outside of your car. Electricity always wants the easiest path to ground. Okay. So let's stop here, and tomorrow we'll start with charging by induction. And then we'll move on to forces between charges and in the electric field. So let's stop here and have a good day.